Uh, my name is Mikhail. I'm software engineer in NVIDIA. And today I will talk about Active Messages API in UCX. And we already talked about that last year on face-to-face, but we made some progress since that. So today we will try to encourage people to use Active Messages instead of other APIs if they plan to. And since it's UCX API, I will start briefly with UCX. And UCX is high performance feature-rich communication middleware, leveraging RDMA performance, but not only RDMA. We can see on this diagram that UCX supports various networks. It supports RDMA, it supports TCP, it supports CRANE interconnect, UGNI, it supports shared memory transports, and also GPU accelerators. And besides that, UCX provides quite rich API. We have different set of APIs intended for different use cases. We have tag matching, active messages, stream, RMA, atomic operations, etc. Maybe that's almost all, but we also have different modes for connection establishment and stream API. And why we decided to talk about Active Messages API, because we see a growing demand for using UCX as a network transport in various frameworks, and which are not really HPC frameworks like MPI or SHMEM. And traditionally, for implementing two-sided communications, we used tag matching API. Let me try to highlight it. Never mind. Sorry. Okay, so we used to use tag matching API, and the reason for that was that it is the most mature API which supports the majority of UCX features. And I should have said that it was the most mature API because now we have brand new Active Messages, and which we will discuss on the next slide. And since I have mentioned that tag API was used in many frameworks, I would like to compare tag API and Active Message API in terms of supported features in UCX. And we see that both of these APIs support the most important for performance features like Rendezvous protocol, multi-rail, when a single message can be sent through several network adapters if more than one is available. Both of these APIs support GPU memory, so we can send and receive to and from GPU memory. And then we see some difference. As it's quite obvious, Active Message API doesn't support tag matching, but here I would like to highlight that this is most probably an advantage for those frameworks which don't really need a tag matching, because it allows to avoid additional overhead needed for tag matching itself, for maintaining expected, unexpected queues, etc. So this overhead is quite noticeable. And with Active Messages, it is possible to do zero copy on the receiver even with Eager protocol, because once the message arrives on the network, we pass a pointer to the network buffer directly to the user callback without any extra memory copies on its way through the stack. And that's another advantage, which may provide quite good performance for small messages, especially for small messages. And with Active Messages, we can send additional user header together with payload, and this change was motivated by certain input-output storage application, and also by PS Lite, which we were talking about yesterday. And I will remind that in PS Lite we have to send a short metadata with every payload message. So and since PS Lite is implemented with tag API, we have to do two sends. One is for metadata and another for payload. And with active messages, it is possible to invoke just one active message send, providing a metadata together with payload in it, and it will be bundled to a single message in most of the cases. And also, it is important to note that with Active Message API, it's much easier to implement full error handling support, because with Tag API, we also support error handling, but there are some corner cases which is very difficult to implement with tags without breaking backward compatibility or introducing significant performance overhead. And this is driven by the fact that with Tag API, we always receive messages to the specific worker. We don't receive messages on the endpoint. And if some endpoint fails, and we detect that our peer failed, it's not that easy to associate all the ongoing transactions with that endpoint, because on the receiver side, we receive everything on the worker. So that was an introduction so far. And where we see active message can be useful. As I mentioned already, it can be useful in almost all frameworks which would need two-sided communications, but they don't really need tag matching. For instance, cloud storage applications, and in our repository in UCX, we have an example, which is called the IODemo example, and we have active message pass in it, which is being actively developed now, but still not mature enough. Then it can be useful for Spark, GPU, and Rapids, and it's already used there. And it also can be useful for PS Lite, and we designed some features in active messages specifically by PS Lite example, but originally PS Lite was implemented with tag APIs because active message was not mature enough at that time. For instance, we didn't have Rendezvous protocol, and without Rendezvous protocol, it's not possible to get a good performance for big message sizes. Also, it would fit very well Charm++, and we have a working prototype, which is not upstreamed yet. So we also have a prototype for GasNet, conduit. And I think it can be useful for implementing various collectives, and specifically in UCC. And let's move to the basics of Active Messages API. As it stands from the name, Active Messages API is driven by the messages, and there is no real receive on the target, on the peer. With active messages, we just register message handlers, which means callbacks for specific active message IDs. And on the sender side, we send some payload and specify active message ID, which is just an integer. In our API, it's 16-bit integer, I guess. So we're supposed to support about 65,000 of message types, which seems to be more than enough. And on the receiver, we just register callbacks to handle incoming messages. And once the message arrives, this callback gets involved, giving us a pointer to the message and some auxiliary information which can be useful for parsing it. For instance, currently we support reply endpoint parameter, which means that sender may it may send a message and saying that I want receiver to get a proper endpoint in its callback to be able to reply to me. And then when the message arrives and callback gets involved, user also gets a pointer to the endpoint, which he can use to reply something back to the sender. And also with active messages, we can specify what protocol we want to use for sending, either eager or rendezvous. It's not possible currently with tag messages because this switch is transparent for the user in tag API, and it's handled inside the UCX. But we exposed this term eager and rendezvous protocol with active messages API because because with active messages we have additional and different APIs for these protocols, and I will explain it further on the next slide. And as I briefly mentioned, when we get a callback invoked on the target, we may receive some auxiliary information like endpoint, which can be used for replying back to the sender. And also we can get a notification whether we just got a real data with eager protocol or with just a rendezvous descriptor, or we just got a rendezvous descriptor, and I'm going to explain it shortly. And also another important thing with active messages, that once we get the data in the callback, we can ask UCX to keep this data for us if we need to use it later, if we can't handle it right now. And to manage this, we use return codes from the callback. So if the user returns OK from the callback, it means that data is not longer needed and UCX can free it. But if we need to keep the data, we just need to return UCS in progress. And UCX will not reuse the network buffer until we free it with another special call. And it may be very useful because we get a network buffer with a message without any copies on the way. And if we can't handle it immediately, we can just ask UCX to keep this data for us and just keep the pointer to it until we're ready to use it. And no any memory copy is needed here to keep the data. And a couple of words about the rendezvous protocol. It was not easy to implement rendezvous protocol for active messages because there is no term receive with active messages. We just get message handler involved when the data arrives, while rendezvous protocol assumes synchronization between sender and the receiver. In a nutshell, rendezvous protocol means that the sender sends some auxiliary message to the receiver before sending the real data, saying that, okay, I'm ready to, I have some data for you, please react when you're ready. And the implementation of protocol really depends on the so-called sub-protocol, because we can implement rendezvous in different ways, but the main idea is that sender synchronize with the receiver before sending the data. And here it's example of how rendezvous is working with some RDMA transport like RC. When we send a relatively big message and UCX decides to send it with rendezvous protocol, at first we just send an auxiliary message which is called RTS, which stands for ready to send, where we send some auxiliary data, such as, for instance, local buffer address and its remote key, so that when a receiver gets this information, it could invoke RDMA read for this data immediately. And as I mentioned, with active messages, we also can bundle some user header with this RTS message, and which suits PS Lite quite well, that we can bundle metadata with RTS in one message. And this metadata would be header on this slide when we invoke UCP IM send on BX. We can specify metadata as a header and payload as a buffer. So the RTS arrives to the receiver, and in this case, we inform user that it's not a real data, it's just a descriptor which allows you to receive the real data, and user has to call active message receive to actually start receiving the real data. And it would look like depicted here. So callback gets invoked. We inspect the flags in this callback, and we see that we just received the data descriptor, not the real data. So we have to invoke the receive call because we need to instruct UCX to what buffer we want to get this data, because this is the purpose of this protocol, to make it zero copy on the receiver. Thus, receiver have to inform UCX what buffer to use for getting the data. So we call this receive with user buffer, and UCX starts doing its normal rendezvous flow. It gets the data using RDMA read primitive, and then informs the sender that, okay, I'm ready, I got all the data, you can reuse your send buffer, you can complete the send request. And it's worth to note that it's not required to call this receive function inside the callback. It may be the case that when the callback gets invoked, user is not ready to receive the data yet. For instance, user doesn't know its receive buffer. So it's also possible to postpone this receive. We just need to say UCX back that, okay, keep this descriptor, I will call receive later, and we can do it with return code as with Eager protocol. And then when we are ready, we just call this receive data, providing the pointer to this descriptor. And actually, the performance of active message rendezvous is comparable to tag API. It's almost the same because underneath they use the same general flow of rendezvous protocol, only the upper layers are different. We may notice some a little bit better performance with small messages because of lack of tag matching, but since rendezvous protocol is mostly used for relatively large messages, it's not that easy to get that benefit, but still possible. So now I would like to say a couple of thoughts of what we are going to do next, because we still have some plans to do. And at first, we want to support multi-fragment Eager protocol efficiently. And I need to say a little bit about multi-fragment. What it means that with Eager protocol, UCX cannot send a message bigger than a certain limit, which is mostly driven, for instance, by InfiniBand architecture constraints, that we cannot send a buffer bigger than the receiver is ready to get. So we have some limitations for the single message. And if someone wants to send an Eager message which is bigger than that limit, we use so-called multi-fragment protocol in both in tag API and active message API. And so far, it is transparent for the user, because on the receiver side, user always get a single active message handler for any Eager message, even if it was delivered with multiple fragments. And how we achieve that, we assemble the message on the receiver, which means that once we get a first fragment of the message and we see that there will be more fragments, we allocate a buffer, and then we start assembling the message into this buffer, which means that we will do extra memory copies for every fragment. And once all fragments arrive, we assemble the message, we invoke user callback providing the pointer to this to this allocated buffer. And as it's obvious that it's not really efficient in terms of performance, because we have to do memory allocation, we have to do memory copies to move all the fragments to our allocated buffer. And in addition, for instance, if user wants to store this message in some internal buffer, it will have to do another memory copy. And we were thinking of how to solve that, and the only solution we see so far is to expose multiple fragments in the API as well. And there is already opened PR for that, for the API, which is still being discussed, but you're free to comment on this if you think something needs to be changed there. And basically, this PR suggests that we define additional flags in the user callback, and once message handler is invoked with the flag that the first fragment arrives and we expect more fragments, we would be able to call receive function and provide our own buffer, and UCX will assemble the message in that buffer so that UCX can use user-defined buffer instead of its own allocated buffer to assemble the message. That's one use case we want to introduce in this API extension. And also we would like to expose just fragments to the user. For instance, if user doesn't need to store a message in its buffer at all, and it's enough for him to use network buffers provided in the active message handler callback, we can just invoke active message handler callback for every fragment. User can handle it and later release these buffers. And in this case, we will preserve several memory copies on the receiver, even with multiple fragments. Of course, it's supposed to be quite efficient in terms of performance, but our main concern is that it complicates API quite significantly, and we would really want to keep it as simple as possible. Otherwise, users will not. I'm not sure user will not benefit from it. It will be quite hard for them to implement everything correctly. So that's why this PR is still under discussion, and maybe we are open to any ideas on how to implement it better than it's proposed in this PR. And another use case we have for active message extensions is so-called fetch API, and it's also driven by IO storage use cases. And what we want, we just want to do, we just want to optimize certain patterns, like read pattern available in our IODM example, or pull pattern from PS slide. And these are similar primitives, which means that sender requests some data from the target, sender of the message. So originator asks target that give me some data, and currently it can be implemented like sender sends an active message saying that, okay, I want some data, and target gets this message and start sending the data with Rendezvous protocol, which means the target will send an RTS and originator will perform RDMA read following by acknowledgement this data. And as you can see on the diagram on the top, on the right, it requires quite a few auxiliaries, additional steps before originator gets the data. And in theory, it could be more efficient if the originator sends with this pull request, originator sends its auxiliary information, which would allow target to perform RDMA write immediately to the originator memory, which means that we would like to be able to send originator address and remote key to the target, and target would do RDMA write, and that's it. It would be less steps, and on the networks, on the scale where we have several hops between the peers, it may be quite noticeable if we get rid of several additional messages of several round trip types. And we have a working prototype, and we had a PR for that, which is currently closed. We closed it because it complicates API quite significantly as well. And the same pattern can be achieved by using different APIs. For instance, we could do similar things if we mixed RMA operations together with active message or with tags. At least two different APIs need to be mixed to achieve that. And from the one perspective, it's advantage and disadvantage at the same time, because we can achieve this pattern with current set of APIs, but from the other side, we have to use different APIs, which might be confusing for the users, and it could be easier for the user to use one set of API, just active message, to get a good performance for every communication pattern. And here we're also open for suggestions on how to implement it better, because with the approach we propose, there are some obstacles. For instance, we have to introduce a new routine like send reply, but it's not really clear what parameters to specify that, because it doesn't really need an endpoint. It just replies on specific data descriptor, but we don't have any sending function without endpoint currently, which is not consistent to the existing APIs. And also, when we use send active message send and DX, we have to say somehow that we are not really sending a data, but sending a metadata about our buffer for the receiver to be able to directly write to this buffer. And we tried to define new fields in our extendable parameter structure, which is intended for such cases, but it didn't look really good. It didn't look clear enough at that time. So I think probably we have to revise that. And I was quick. I mean, that's all I have for today, and we can move to the questions if any.
Alrighty. Thank you for the presentation. Do we have any questions?
Yes, I have a question, actually not for Michael, but for mostly for the users of Active Messages. If it makes any sense to introduce some kind of ordering flags for Active Message sends, for example, because, for example, if we don't mandate a strict order between Active Messages, we could use multi-rel more efficiently, potentially use a UCT transports that do not have strict order in some cases. But on the other hand, probably some use cases of active message do require strict order. This is somehow related to how we choose to implement multi-fragments, because fragments can potentially arrive out of order, so we have the offset there. But if we want to also support out of order on the first active message that contains the header, it would be more challenging to match between the message itself and the fragments that come after it.
Yeah, today in UCXPy, we definitely rely on ordering of messages, so that could be problematic for us.
Yeah, seems like if there would be a out of order option, it's have to be something you'd have to opt into rather than
Yeah.
being.
Yeah, I agree.
Okay.
Yeah, I guess then we have to maintain the ordering because it would be harder, I think. And if somebody needs out of order, sorry, if somebody doesn't need ordering, we can think about adding an option, right?
Yeah, I'm asking mostly because it can affect the multi-fragment API. Because if we do plan to allow out of order in the future, we need some kind of message ID to know to which header every fragment belongs. But if we, let's say, if we said that we never want to introduce out of order support, we could just do it according to the order or something like that.
Yeah, I think
what granularity are you thinking of? Like, is this on a worker basis or a message type basis? Like, how would we enforce the ordering? Like, at what?
A good question. So, obviously, the most useful would probably be per message.
Yeah, I
but
agree.
But sometimes it can affect the transport that we select. Maybe we can consider having a set of lanes. It doesn't have to be necessarily a disjoint set, but a set of lanes for a forced order, a set of lanes for a loose order.
Mhm.
But also, if we're talking about order and multi-fragments, it's we kind of have to distinguish two different cases, whether we're talking about order for the message or we're talking about order for the fragments. Because
I think for the fragments, we never plan to guarantee order and just provide the offset, right?
Yeah, then probably then what is needed for what is needed additionally for out of order? I didn't get it.
And so we need to make sure that the way that we match between fragments and the header can withstand adding out of order to the header. Like, did you plan to use a message ID or something like that?
You mean that receiver needs to understand?
Yeah.
But if we implement it this way, that sender informs the receiver whether it has to be out of order or not. But I think it's more important for receiver to specify whether it's ready to receive out of order messages or not. And in this case, we could make it a flag for registering the active message handler or something like that.
I think maybe for the receiver it would be too late, because if it's not Rendezvous protocol, the receiver is not communicating anything to the sender. So how would the sender know which method to use for sending?
All right. But no, this may be relevant if we really implement it this way, that we have different set of lanes for in order and out of order transfers. But if everything will be decided on the receiver, then maybe it will not be necessary for sender to know anything, because we can implement we can maintain the order on the receiver, right?
You mean that sender would have to send sequence number in any case?
Yes.
and the receiver would choose whether it would do something with it.
Yes, I think so. But we already do that. If I'm not mistaken, we send a message ID. So in the receiver, we can define whether we want to order them somehow, or we can just invoke user callback once something arrives.
Oh, but if you're doing this already, isn't it something that user handler can already do? If it's purely software thing, I think it would be valuable if we can, at least in some cases, rely on transport order.
With current API, user handler can do nothing because we don't invoke active message handlers until we assemble the whole message.
Yeah, but I mean, if we're talking about the future case with multiple fragments only.
But last time we discussed that, we were going to, by the way, let me move to the slide. We were going to provide a message context to the user callback, so the user callback can associate this context with every other fragment.
Okay, so I think it should be fine then.
Yeah, this is what proposed in this PR. And if we decide that ordering is not really needed, ordering is not, I think we have to think a bit about that. But so far we have a use case where ordering is really needed, as Peter mentioned. So far 1 versus 0. We have one use case for ordering. In our demo probably we don't need ordering, right?
Yes.
So it's 1-to-1. So definitely need to sync.
Also for Spark, I think we don't need ordering.
I think the first thing which needs to be clarified, what performance we can get with introducing out of order.
Yeah.
I mean, it may appear that we don't get any real benefit with out of order active messages, but we will have to maintain bigger code base and complicate the API.
Can I ask some basic questions to clear my understanding of these ordering requirements? So currently, 2 UCP active messages can be sent by a sender to the same remote worker address with the same AMID, and then they could be received and processed out of order by the receiver, right? Is that correct?
By default, it's not. By default, it's not correct. It's not possible. Order is maintained.
Wait, Michael, what if they have a different size? As first message is multi-fragment.
First message. Yes, but by default, multi-fragment is disabled for eager. That's
Right,
why.
but it means that the first we would have to wait until the first message is assembled, and then we call it. In the meantime, the second message has not even arrived, right?
Yes. But
Is it possible we have some kind of multi-rail?
yes, if multi-rail is supported for active messages for both eager and rendezvous, but like with tag API, it is disabled by default for eager protocol. And if you enable it, yes, you can get eager messages out of order.
One more quick question on that ordering aspect. If there are 2 different transports selected, because even let's take out even multi-fragment out of the question. If there are 2 different transports selected just based on the size, say one goes over shared memory and one goes over RC, is it not possible for things to arrive out of order?
No, because you said that we are not considered multi-rail, multi-fragment, you said we're not considering multi-fragment, right? No, it's not possible if we're not considering multi-fragment, because eager protocol is implemented in a way that first fragment is always sent through the same lane, through the same transport. And even if you have different lanes for sending active messages, the first fragment will always go through the same one. That's also.
I meant to say, what if there are no fragments? You just end up issuing two send NBX operations. First message is a small message, which would by default go over eager protocol, and second message is a large message, which could, which I suppose won't go over Rendezvous protocol unless requested.
Okay, so it
in
will
this
be.
case, is it possible?
User callbacks will be invoked in order, because for sending Rendezvous RTS messages, we always use active message lane. And this comes from Tag API, where ordering is very important. And in active messages, we reuse almost all the infrastructure for eager and Rendezvous protocols. And in your use case, we will send both messages through the same lane. I mean, we will send small message through the active message lane, and then we will send, you started with big message. So we will send Rendezvous RTS auxiliary message through active message lane, and then we will send a small message through the same lane. And on the receiver, user will get callbacks in order. But when the user starts receiving Rendezvous message by invoking special receive call, it will use may use different lanes, like RMA bandwidth lanes, but in this case, ordering is not important already. Is that clear?
Yeah, that makes sense to me.
Yeah, I have two more questions about that. So does all of this mean that we can guarantee the user that 2 UCP AM messages sent will be received in order and processed in order at the receiver side? Because
Yes.
it is my understanding that we don't have that, because we have UCP worker fence as well, and it doesn't even apply to AM messages. So do we have any ordering guarantees for UCP AM messages to the user?
Yes, we do have this guarantee right now, unless we enable multi-fragment for multi-rail for eager.
No, I mean, because UCP user doesn't even understand eager or Rendezvous, right? It just sends a UCP active message and has a handler at the receiver side.
Unfortunately, or fortunately, with active messages, UCP user has to understand it because it's exposed in API. You can specify exact flag in sending function which protocol you want to use, and we had to
enforcing eager or Rendezvous.
Yes, right? Yes, and we had to expose this because there was no any other way to implement Rendezvous protocol. On the receiver, user has to distinguish eager and Rendezvous to be able to understand whether it just received real data or just an internal descriptor which needs to be used to get the data.
That's right. So let's assume user doesn't specify any flags when sending an active message, but I understand that the receiver side in the handler, you have to check the flag to see if this is Rendezvous or not.
Yes.
Then what are the ordering semantics here? Then we say if you send if you receive everything eagerly, it is in order, and if not, it might not be.
Not really. As I mentioned, ordering is maintained currently until you enable multi-rail for eager protocol, which is disabled now. And even if you mix big and small messages, or if you mix sending with different flags, eager and Rendezvous, the callbacks, active message handlers on the receiver will be invoked in order. In order they were sent.
Okay, so unless we enable multi-rail for UCP AM, then the ordering is guaranteed.
Yes, for the eager protocol. We have a
For-
common handle for the multi-rail linear, both for active message and tag APIs.
And
I see. And
and the multi-rail is configuration option, or
Yes, it's environment variable.
so then semantically wise, you should decouple from implementation behavior what semantic APIs exposes. So if it's configuration options, then the answer is no, it's not guaranteed. Your application cannot assume behavior of semantics based on configuration options.
Okay,
Because,
let's assume you don't know about
what I
this option.
suggest, you have to decouple from what implementational behavior, which is one thing, and what semantics is exposed to user. In whatever you trickery we're doing with configurations, that hey, I disable the multi-rail, and now it's in order. It's again, it's influencing internal implementation. Semantics, they should assume there is no order.
I agree with you here. There is a little bit of mess in these definitions currently. That's why we want to introduce this extension, which would define ordering, fragments, etc. And we would really like to get any feedbacks on that, maybe in this PR.
Well, I think we can define it as today again. The fact is, order is not guaranteed.
Yeah, but it limits
we-
our users.
And we can, like, in users taking advantage of certain implementation, version. But and from here, okay, let's assume no order, because we have other APIs where tags APIs, right? Where definition of function explicitly defines the ordering rules. Here we didn't have any ordering rules defined. So it's out of order. And like next step, it will be okay if you want to provide user with the flexibility of have some control over ordering semantics. We introduce this extension, and we'll introduce ordered semantics in addition to out of order, which it's what it is today.
Yes, formally it's true, but I'm not fully agree here because it would limit the potential users from using Active Message API now and providing feedback. For instance, Peter can use it because multi-rail is really disabled by default since the beginning and nobody uses it. And without it, it's really, ordering is really maintained. But it's not clear, I agree, and we have to define.
Well, and somebody will download the code and set different variables because they have two nicks, and the code will explode and your assumption will break. So again, like, yes, I agree with you, like there is certain, corners of implementation, people take advantage of it and leverage this. So the way to fix this is, I'm not suggesting ignore it and say it's out of order and now Peter deal with this. This is not the intent. We have to, if there's applications that want to take advantage of ordering semantics, we have to define it through API. And I think it's where you're going with your proposal. And let's start with the assumption it's out of order today, and you introduce additional flags to enforce order, and potentially it will have performance hit because multi-rail will be disabled, blah blah blah. But they will want the behavior they want.
Okay, maybe here's some Akshay and Peter. Maybe we can have a chat or meeting to clarify what you really need or want from Active Messages for us to go in the right direction with this ordering definition.
Sure, that sounds good. I think both Hassan and I were coming from the viewpoint of what should we need to implement in EFA in order to guarantee that AM messages are ordered. But from earlier description you provided, it seems like as long as any transport provides the necessary implementation to do zero copy transfers, ordering is guaranteed outside of that because there's ordering through callback invocation that essentially guarantees it. But as Pasha mentioned, there could be issues with multi-rail as well. So that's something to be considered.
And with multi-rail disabled for the eager protocol, the ordering is guaranteed for UCP AM only if the underlying UCT AM guarantees ordering. Is that right?
No.
I mean, do we not rely on UCT AM guarantee ordering?
No, we don't, because, for instance, if you enable multi-rail, if you have multi-rail, for instance, you have two different transports. You have two lanes. For instance, ordering is guaranteed on each of them, and then you send two messages, one big and one small. And you send a big message, you send the first fragment and start sending second fragment on the second lane. And then you send a small message on the first lane, and it arrives earlier than the big message gets assembled on the receiver. Because you have different lanes for transferring message, and with multi-rail, a big one can be transferred through different lanes.
Right, but if I disable multi-rail, because let me ask my question this way: do we have any ordering requirements for UCT transports? For UCT AM API?
I see. Yes, we rely on that, because if UCT doesn't provide ordering, then UCP doesn't provide ordering as well, even for single rail.
Right. Okay. Yeah. So UCT AM guaranteeing ordering is required for both UCP AM and tag messages.
Yes.
Okay. All right.
Yes. Basically, UCP AM is using almost the same infrastructure for eager and Rendezvous. At least for Rendezvous, it almost reuses the whole infrastructure, and for eager, it reuses some parts, but the idea is similar.
Right.
Some babies really unhappy with the ordering semantic.
Yeah, sorry, this is mine. This is mine.
All righty.
So I have one question, Mihail. So what is the next step? We will take the discussion to the mailing list with proposed options.
We can try that, yes, because I think the first problem we have to solve is this multi-fragment and ordering issue, and we already have open pair for that. It was just postponed a bit due to other activities, but probably we have to resume discussions there. And maybe it's worth sending a mail to the mailing list, but the problem is quite complicated, so it has to be clarified. And I see Sergey has some question as well.
Yeah, I have a real quick question. So in the beginning, you mentioned that Active Message supports both host and GPU memory, but my question is, does UCX support both Rendezvous and Eager for GPU memory?
Yes, and sorry, I forgot to mention the work we did since last year, and now GPU memory is supported for any protocol, and active message alignment is also supported. The user can specify the desired alignment and how it works with Eager protocol, because in UCX, with Eager protocol, messages always arrive to the CPU buffers, because we proposed balanced buffers allocated on CPU memory, and user will get a pointer to the message in CPU memory, but then user can invoke this IM receive message specifying a GPU buffer, and UCX will unpack the memory from the CPU to GPU buffer.
So it's an additional copy anyway.
Yes, it's an additional copy anyway, and otherwise you would better use Rendezvous, because to implement zero copy to GPU memory with Eager, it would be kind of implementing another UCX, or maybe a little bit less complicated, but we will have to implement bounds buffers allocated on GPU. And this is quite big effort.
Okay, makes sense. Thanks.
So Michal, I think it will be good to send the RFC on the mailing list to discuss this and see how we go. As people brought up, like if SDR is completely out of order, as far as I remember, TOEFL presented earlier, also very lax order. So we'll have some other transports coming up with very relaxed ordering semantics.
Okay.
Which imply you'll have to do much more work on UCP to assemble everything in the right order. So I would suggest to start RFC, and this is a big topic, continue discussion there.
Okay, I see. And the biggest problem which prevents us from progressing here is as we try to maintain simple MPI but make it flexible. And it seems to be not possible really, because we're trying to define new things and it really complicates the API.
And maybe solution will be to define other API.
Maybe it's better to define another API function than complicating the existing one, which maybe it would be simpler.
Okay, so I think you have the next steps, right, to bring it on the list and continue brainstorming there.
Yes, thanks all for the comments.
Cool, really good stuff.
So I stop my presentation now.
All right.